Sounds good. Thank you, Beth, and thank you again for allowing us to present some of our thoughts on this project. My name is Mersim Regimentovic. And everybody can hear me, okay? Just to confirm, right, before I get too into it.
Yeah, all good. Can hear you just fine.
Perfect. Today I'll be presenting on distribution network information modeling project, which we've collaborated with SGN on. And yeah, if we can go to the next slide, please. Next slide, please. Yeah. So in August of 2021, the UK unveiled an aggressive strategic energy policy transition to a world-leading hydrogen-based economy. These policies set out to reach net zero by 2050. For gas utilities, this represented a powerful shift from methane to hydrogen-based energy ecosystems that have introduced a variety of questions regarding cost effectiveness, safety, and risk mitigation. So prior to that transition, gas utilities would be tasked with demonstrating the economic benefits of utilizing existing network infrastructure with hydrogen compared to laying new electrical-based heating infrastructure. And so, as you can imagine, really the kind of two core, questions here are, how can we use the existing gas network infrastructure, and what's the cost associated with doing so, and what are the safety risks to consumers, and how can we mitigate those risks before injecting hydrogen? So for the latter, we use the example of, as we begin to inject hydrogen, every consumer will need new appliances. And so if there are unknown parts of the network, how can we mitigate those risks and ensure that we're pumping hydrogen into the network, and knowing all the paths of the hydrogen within the network, so we can ensure that the consumers were adequately prepared to be safe when this hydrogen injection takes place. So in the case of current gas utilities now, for example, for SGN, in the case of SGN, there are 74,000 kilometers of pipeline, and ensuring they're resilient and robust ahead of this transition is a really important feature of the transition to hydrogen, and ensuring that the 5.9 million current customers are able to safely take that hydrogen into their homes and be able to use it. Currently, there is no viable method for collecting this data on a time or cost basis. So, and if you could imagine mapping the whole network to ensure that all of the taps and joints and all of this huge amounts of metadata are considered as part of building this economic model, that would take a substantial amount of, in the case of push rod camera inspection and things like that. This would be highly disruptive to consumers and very costly to gas utilities. So to address this, we were proposing the development of a Dnim robot. Dnim is our distribution network information modeling system. And this is a robot that is an autonomous tetherless robot that we're proposing to deploy into the live gas mains to map the network from inside the network, thus allowing gas utilities to perform this mapping without the disruption, without the substantial cost to consumers. All right, if we go to the next slide, please. So in the current gas pipe records are just an amalgamation, really, of analog information from the time that they were laid down. So in the case of gas in the past in the UK, for example, could be upwards from 1880 onwards. So there are new mapping initiatives, as in the case of London, where we're beginning to digitize these network. In the case of London's underground, digital initiatives. And in this case, they offer a lot of opportunities for us to close gaps on some new pieces of information. So as you can imagine, some of the current data to date may kind of share kind of what the size pipe is, what material is, but there could be, there are gaps associated with what are the joints, what are the taps, and as we kind of shift back to the economic assessment model, gas utilities will be tasked with kind of understanding what is the cost to repair and remediate their network ahead of these, the hydrogen injection, and what is kind of suitable and what is not suitable. Are there any high risk features? What is the cost of repair and or remediation of those features? So this is kind of what we would call here is now building this business information modeling or building information modeling. So some people may know the acronym BIM. And so, this project marks a vital step to strengthen the UK gas network's robustness and enable this transition, and ensure the safety to the end consumers. We go to the next slide, please. So, as I mentioned, really the goal is how can we collect this data and how can we kind of close the gaps on some of the kind of really critical pieces of data as we digitize the network. So in the case of some of these, higher risk features, joints, taps, plugs, any unknown parts of the network, how can we collect that data and how can we stream that into some sort of GIS system that has, these BIM level outputs and, obviously its alignment to some of the ongoing digital initiatives in London and across the UK as well. But really kind of using this is also an opportunity to that could in the future be deployed to other pipe networks. But as we kind of discuss this with respect to making, ensuring the resilience and robustness of the gas networks, ahead of the transition, it can also potentially be used as a tool for ongoing construction and maintenance as as we kind of move past the hydrogen injection point. So really kind of powerful problem for us to solve with this kind of autonomous tetherless robot. So if we go on to the next slide, please. So that kind of brings us to our current project. We're delivering this discovery phase. Previously, ULC and SGN have completed early stage R&D projects where the conceptual pipe mapping method was investigated and has been defined as Dnim. Again, Dnim is a proposed tetherless robotic system that can perform the network mapping from inside the pipe. When combining this advanced mapping techniques in conjunction with machine learning-based feature detection, gas utilities may identify and quantify the cost of repair and remediation of these high-risk features in their network. Meaning that as the robot is beginning to scan, we can not only have the robot effectively know where it is, but also identify where these features are in respect to the network and be able to kind of attribute some cost of repair accordingly. So this, these outputs have the potential to allow us to digitize the network through kind of these, again, building information style models, where we're having these 3D models with these machine learning based feature detection and categorization. So this work focused on, in the discovery phase, focused on the business engagement on SGN side through their organization about where can this technology offer benefit, and so that they've kind of reiterated their commitment to continue and pursue this and move forward with the Dnim project. As far as the alpha phase, kind of our focus here was preparing this roadmap for development through alpha and beta phases and showcasing some of the works that we've previously done. And as part of this project, this was a no cost submission from SGN and ULC to kind of show that commitment through to SIF. So if we now kind of get into the next slide where we can kind of start discussing some of the more technical aspects. So ULC Technologies has been has over 20 years of experience of developing these robotic solutions and deploying them in live natural gas environments, and we really do so by really two teams, one of which is our R&D team, one of which I work on, and the second of which is our field services team. So during this 20 years, we've developed a significant amount of expertise in machine learning, computer vision, which are really core capabilities and core skill sets needed to drive this project. And so in this case, we're looking at just some examples of the AI and machine learning models that we've developed in the past. So in this case, this is a live gas main, and this is kind of just some of the first instances of the first cog that would kind of drive home this project. So being able to process some of the video footage from a robot inside a gas main and identify, in this case, some examples of joints and taps in the environment, in which in previous cases where a person would have to kind of sit there on a truck in a cordoned off part on the road and sit there and review that footage for 4 hours or however long it would normally take. So this proposed technology for Dnim is comprised again of these two core features: the accurate localization, and secondly, the use of machine learning to identify these features of interest. So this is just again an example of some work that previously ULC has developed and kind of one of the core technologies to be used here. And so if we get into the next slide, please. So again, Dnim is the distribution network information modeling. So Dnim is a multi-robot system whereby two robots are collaboratively mapping infrastructure. This proposed approach is done by having these advanced localization capabilities as well as the use of machine learning to categorize these pipe features. The proposed robot is tetherless and autonomous and can travel into the network to collect data, thereby kind of reducing the overall or potential overall number of excavations required to perform this assessment. So Dnim offers a safe, accurate, and cost-effective asset surveying solution that will help Great Britain's gas networks undertake a full economic assessment of their networks while maintaining the supply of or the security of supply. As I mentioned, this can be potentially done in live gas. The results of these mappings have the potential to provide the knowledge-based information required to undertake large pre-construction works on natural gas infrastructure ahead of the conversion to hydrogen. So, for example, what plugs and what fittings need to be replaced. Essentially, what sections of the network are metallic, what joints need to be remediated, et cetera. And so this project will also generate key learnings around the latest 3D mapping technology and machine learning for use in mapping and other applications. So in addition to kind of the greater level accuracy existing networks, along with the correlation to above ground infrastructure, this result provides SGN's design and planning teams the potential to design gas mains replacements projects with the least amount of excavations required, or the greater use of keyhole technology. So this would greatly improve the customer disruption and increase the efficiency of planned works. Moreover, repair teams could also utilize this mapping platform to identify features in the range of reported gas escapes, blockages, et cetera, and resulting in a kind of a low-cost solution that could increase the use of keyhole technology and decrease the size of traditional excavations. We go on to the next slide, please. So in this case, now we're looking at in the case of the in the case of the collaborative robot, we're looking at the face of the projected light or projected laser. In this case, we're using this mathematical algorithm to track the position of these lasers and providing very accurate localization. This generates a 3D point cloud. So this figure on the right side you see is, in this case, is still 2D image, but it would be what would be a 3D point cloud. And so you can turn it and see that, generally speaking, that it could potentially be 3D in nature. If we go on to the next slide. So that was really the first cog is that accurate localization. The second cog is now once the robot is effectively localizing in the gas network, how can it collect data for these features of interest that have historically not been captured on traditional drawings and such. And so in this case, we have a secondary camera system that can take these high resolution videos and be later processed in machine learning to identify, in this case, joints, taps, or potentially other high risk items. And so really when we have these two data sets taking place, we can have this process take place with limited or with significantly reduced disruption to consumers. Making this a tetherless system allows the system to navigate deeper into the network and thereby reducing, again, the overall potential number of excavations to make this assessment. We shift into the final slide. So Dnim will deliver value directly to the gas networks by reducing theft of gas, as well as decreasing the cost for customer connections. Furthermore, Dnim will offer future savings to consumers by enabling superior energy models. This will reduce the spend on upgrading the network for future energy scenarios and ensuring the robustness and resilience of the energy system. Having this fully digital record of the network could also allow customer inquiries for new connections or alterations to be delivered through the use of smart engineering and commercial models, thereby reducing SGN's cost to serve and other gas networks' cost to serve, creating savings for the consumer. So kind of as far as our next steps, we're looking to kind of progress and prepare a proposal for the alpha stages for validation testing and some updated conceptual models of the system. So Beth, that was kind of all I had on my end. If we can kind of shift into the questions, I think we're right at time.
Brilliant. Thank you so much. Actually, my background is kind of robotics and stuff as well. So that was really, really interesting. We have 2 questions so far. So are there any locational or physical barriers to this project in terms of areas that the robots perhaps can't assess, maybe due to legacy sections of the network, or maybe the pipelines are too narrow?
Definitely. So great question. So really the physical barriers would be related to just the size of sensors. And so as you can imagine, the size of sensors can preclude it from accessing very small pipe sizes. So that may result in kind of a different technical approach. Or, conversely, if there are reducers in pipes or things like that. But generally, for the latter, there may be opportunities to just structure, the deployment or the excavation in a manner such that the robot can travel from the smaller pipe into a larger pipe.
Yeah, yeah, no, really good. And perhaps an opportunity to link up with maybe other projects who are looking at maybe sections of smaller pipelines and things like that, and sharing learnings there. Brill. So the second question is, can you outline the innovation in this project in terms of what are the significant risks that are needed to be overcome? And why can't this be adopted as business as usual yet? What is the process there?
So I guess the innovation, I guess the core challenge here is the work associated with two gas networks to perform this level of mapping is very intensive and very disruptive. And so, as I mentioned earlier in the call, the 74,000 kilometers of pipeline, to inspect that with pushrod cameras, that's a lot of inspections. That's a lot of, essentially could be knocking on people's doors, accessing their basement or accessing their meter box. Very disruptive, very costly. So kind of the overall goal here is how can we make this tetherless autonomous robot inside the pipe, send it inside the pipe and potentially allow it to map for some extended period of time, to thereby kind of capture a greater portion of the network with limited disruption to consumers. As far as its use as a kind of, or its potential as a business as usual project, the challenges here, there are technical challenges here. So this is for example, 3D mapping and things like that. This is too high of a risk profile, I would say, for most BAU projects. And so that's why it's best suited, generally speaking, for SIF, who is looking for kind of these innovative, transformative projects.
Thank you so much. We still have a little bit of time. So just because this is my area of interest, so there exists quite a few robots, I would say, that are simply one device which travel through either tethered or untethered. So what's the actual benefit of having two side by side going through simultaneously?
That's a great question. But so really I guess the proposed approach here for the multi-robot system is a result of some challenges in the mapping technique. So in the case of some of the pipes, there just are not a lot of kind of visual features inside the pipe, and so we kind of generate this visual feature to be able to more effectively map the pipe. So if you could imagine, maybe old cast iron may have some features, but maybe plastic may not. And so to map this and be able to perform accurate localization, we just need some sorts of visual features to use as kind of key points as part of the mapping process.